Welcome to this explainer. Okay, today we're going to explore a single, remarkably elegant rule of physics that quietly dictates the world around us. Have you ever wondered what invisible force actually connects a floating ping pong ball, a 300-ton jumbo jet staying up in the sky, and the blood currently pumping through your own heart? I know it sounds like a riddle, but the answer is an absolutely fascinating scientific concept that we're going to break down visually together.
Okay, let's dive into this with a fun little challenge. Picture this. You've got a ping pong ball. How in the world do you make it levitate in midair without using any strings, magnets, or magic tricks? Well, the secret lies in understanding exactly how fluids, and remember, in physics, air counts as a fluid, move and behave.
You can actually try this simple physics puzzle right at home. Step 1, you just roll a piece of paper into a cone. Step 2, securely tape a bendy straw to the bottom so there aren't any air leaks. And step 3, place the ping pong ball inside the cone and blow a constant, steady stream of air right through the straw. Now, your gut instinct probably tells you that blowing air directly at the ball is just going to launch it out of the cone and across the room, right? But instead, the ball actually levitates. It just hovers right there above the paper.
To figure out exactly why that happens, here's our roadmap for this explainer. We'll be looking at the magic of floating balls, meet Daniel Bernoulli, how airplanes actually fly, the Magnus effect in sports, and finally, Bernoulli inside your veins.
Starting off with Section 1, the magic of floating balls. Fast air equals low pressure. Here is the absolute key mental model you need for everything we're going to talk about today. Fast air equals low pressure. When you blow that fast, thin stream of air through the straw, it rushes around the sides of the ball, and that creates a little area of low pressure right around it. But here is where it gets incredibly cool. The normal, slower-moving room air completely surrounding that fast stream, it has a higher pressure. So if the ball wobbles and tries to escape its little low-pressure pocket, the high-pressure air on the outside literally acts like an invisible wall, pushing the ball right back in. It's trapped perfectly by the pressure difference.
Moving on to Section 2, meet Daniel Bernoulli, the mind behind the principle. All right, to really appreciate how universal this is, we've got to step back in time. Bernoulli's principle states that as the velocity of a moving fluid, whether that's a liquid like water or a gas like the air we breathe, increases, the pressure within that fluid decreases. It's essentially a zero-sum game of energy. Now, what's really interesting about this slide is how it breaks down the conservation of energy. Think of a fluid as having a fixed, set amount of total energy. When it's just sitting still or moving slowly, most of its energy is potential energy, exerting what we call static pressure. But the second you force that fluid to speed up, that energy converts into kinetic energy, or dynamic pressure. Since the total energy has to remain completely constant, as the kinetic energy goes up, the static pressure simply has to go down.
This brilliant realization came from a guy named Daniel Bernoulli. Born in the Netherlands back in 1700 into this very famous family of mathematicians, he eventually published his absolute masterpiece, Hydrodynamica, in 1738, which completely outlined the conservation of energy in fluids. But get a load of this twist. His own father, Johann Bernoulli, was actually so wildly jealous of his son's brilliance that he literally stole some of Daniel's key ideas, published a rival book called Hydraulica, and even backdated it to make it look like he thought of the whole thing first. Talk about some intense family drama.
Let's move to and see how this builds into Section 3, how airplanes actually fly, debunking the myths. So, aviation is arguably the most famous application of this principle, but surprisingly, it's also widely misunderstood. The myth he might have actually been taught in school is called the equal transit time theory. Basically, it claims that a wing is curved on top so that air molecules have a longer path, forcing them to speed up to quote-unquote catch up with the molecules on the flat bottom. But that's entirely non-physical. Air molecules don't care at all about meeting up with their old neighbors at the back of the wing. So the crucial point is that lift is actually created by flow turning. The wing's shape and its angle curve the airflow, literally forcing it downward. Think about it. If lift was entirely due to just Bernoulli in that classic curved shape of the wing, paper airplanes with completely flat wings just couldn't fly. Stunt planes wouldn't be able to fly upside down. The truth is, Bernoulli's pressure differences work hand in hand with Newton's third law of motion. As the wing actively pushes the air downward, the air pushes the wing upward with an equal and opposite reaction. But make no mistake, Bernoulli's principle is still absolutely everywhere in aviation. It dictates how wing curvature and angle of attack optimize those crucial pressure differences.
It's also exactly how older piston engine carburetors work. They use a narrowed tube called a venturi to deliberately speed up incoming air and drop its pressure to suck in the engine's fuel. And the craziest part about that? The fast air drops the pressure and the temperature so drastically that those carburetors can actually freeze solid with ice inside, even on a perfectly warm summer day.
Which brings us to Section 4, the Magnus effect in sports, bending the ball.
Okay, shifting gears to sports. When a soccer player bends a spectacular free kick around a wall of defenders, they're using something called the Magnus effect, which is really just Bernoulli's principle applied to a spinning object. Here's how it works. When a ball spins as it flies, one side of the ball is actually spinning with the airflow. This pulls the air along with it, making it faster, which, you guessed it, creates low pressure. Now the other side is spinning against the airflow, bogging it down, slowing it up, and creating high pressure. The high pressure pushes the ball hard toward the low pressure side, literally curving its path right in mid-flight. This physics is so incredibly sensitive that just changing the design of the ball changes the whole game. Remember the 2010 FIFA World Cup? That official ball was designed with a special golf ball-like texture to make it supremely aerodynamic. But that engineering completely backfired. It's truly fascinating because even the world's absolute best players couldn't predict its trajectory. The Magnus effect on it was so wild and exaggerated that it made the ball dip and swerve unpredictably past the best goalkeepers on the planet.
Finally, we reach Section 5, Bernoulli inside your veins. Cardiovascular physics.
We've been talking a lot about moving air, taking this all the way from 18th century mathematics to modern sports. But fluid dynamics applies to liquids too. So how in the world does this exact same physics principle apply to the human blood pumping through your body right now? Well, cardiovascular physiologist Dr. Richard Klabunda explains it perfectly. He says, an increase in velocity leads to a decrease in lateral pressure. And this brilliantly illustrates the basis for the Venturi effect happening right inside your blood vessels. Because blood has mass and it has velocity, it inherently has kinetic energy.
So think about a very real medical condition called stenosis, which is where a blood vessel abnormally narrows. Just like the narrow part of that carburetor we talked about, the blood flow literally has to speed up to force the same amount of fluid through that tiny little gap. As the blood velocity drastically increases, its kinetic energy spikes. And because we know total energy is conserved, the lateral pressure actively pushing out against your actual vein walls drops significantly in that narrowed section.
And this isn't just some abstract whiteboard theory. This is absolutely critical for doctors to know. If a doctor is measuring a patient's aortic pressure, the reading can vary by up to 20 millimeters of mercury depending entirely on how the physical sensor is angled in the bloodstream. If the catheter faces directly into the flowing stream, it captures the total energy, the literal kinetic hit of the fast-moving blood. But if it faces the side of the vessel, it only measures the potential energy, or the static lateral pressure. Understanding Bernoulli's principle ensures doctors are getting the right numbers to make the correct, life-saving diagnosis.
So, from a bitter rivalry between a father and son over 18th century mathematics to reliably lifting massive jumbo jets into the clouds, bending a game-winning free kick, and even diagnosing the human heart, Bernoulli's principle is a masterclass in how fluid dynamics connects absolutely everything around us. So, as you go about the rest of your day, I'll leave you with this to think about. Where else is unseen, invisible physics quietly shaping your daily life? Keep your eyes open and definitely keep learning.